There are 2 trillion galaxies above you right now, full of stars that have never stopped burning. And yet, between every one of them, the sky stays completely black. That's not supposed to be possible. This contradiction had a name by 1823. Astronomers call it Olbers Paradox. Everyone hears the sky is dark and assumes that's simply how space looks. Almost nobody has checked what the math actually demands. 100 billion stars burn inside the Milky Way alone. 2 trillion galaxies fill the sky beyond it. And on a clear night, less than 1/10,000th of that sky shows any light at all. Tonight, we'll trace 3 explanations that seemed airtight and collapsed. We'll land at Bell Labs, where 2 engineers found something living in their antenna that neither of them could explain. And we'll end at a wall 13.8 billion years wide, a wall made entirely of time. By the end of tonight, you'll know exactly what that wall is made of. Space isn't dark because it's empty. It's dark because of something your eyes were never built to see. Let's begin. Pick any point in the night sky and follow that line outward, forever. In a universe scattered evenly with stars, that line never ends in emptiness. It ends on a star, not eventually always. Shift 1 degree to the left, and the same is true. 1 degree further, and the same again. Every direction, without exception, terminates on a burning surface far past what the naked eye could ever resolve. That's the part almost nobody explains. Distance doesn't cancel this out. A star twice as far away delivers a quarter of its light. The inverse square law, unforgiving and exact. But a shell of space twice as far away also contains 4 times as many stars. The dimming and the multiplying cancel each other out, shell after shell, all the way out, which means the total light striking any single point in that sky should also be infinite. Not because the math is exotic, because it's ordinary arithmetic, run out to a distance nobody's intuition was built to travel. If that model were true, the consequence isn't subtle. The entire sky, every point of it, should burn as bright as the surface of the sun. Not brighter in some places and dimmer in others, but uniformly, blindingly bright in daylight and at midnight alike. There should be no such thing as night. Stare directly at the sun for even a second, and the eyes register pain before the reflex to look away finishes firing. Every photoreceptor overloaded by one relatively small, relatively close source. Now replace that single star with the summed light of every star in an infinite, unchanging cosmos, arriving from every direction at once, day and night, with nowhere left to look that isn't equally bright. The room you're lying in right now, dim enough to fall asleep in, shouldn't exist in that universe. There is no curtain wide enough to close against a sky like that. Picture a forest so dense that in every direction the eye eventually meets a trunk. Walk to the edge of a real forest, and gaps of open sky are still visible between the branches. A clearing here, a thin patch there. Now let that forest keep going, past the horizon, past the last road, forever. Every gap closes eventually. A trunk a mile back, a trunk further than that, but a trunk somewhere. On every line drawn outward. That's where you have been standing since the night you were born, asleep, most nights, under a sky that, on paper, isn't supposed to leave behind a single dark patch to fall asleep under. By the early 1800s, this had stopped being a curiosity. It had become a genuine fracture in the working model of the universe. A model astronomers had treated as settled for 2 centuries. Infinite, unchanging, scattered evenly with stars in every direction, forever. 3 assumptions, stacked on top of each other, that nobody had thought to question. One of them had to be wrong, finding out which one would take 3 centuries. Several confident wrong guesses, and one accidental discovery at a research lab that had nothing to do with astronomy at all. The dark between the stars isn't empty, it's just late. Johannes Kepler saw this problem before telescopes were good enough to make it worse. The English astronomer Thomas Digges had proposed something radical a generation earlier. The stars weren't fixed to some crystal shell above the Earth, decoration on a ceiling. They were suns, an infinite number of them, scattered through infinite space, at every distance imaginable. It was a beautiful idea, and it matched what Kepler's contemporary, Galileo, was finding with his new telescope. More stars than anyone had ever counted, hiding in the gaps between the visible ones. Kepler didn't accept it, not because he doubted the mathematics of an infinite universe, but because he'd already noticed the one thing an infinite, star-filled universe couldn't explain: darkness. If Digges were right, Kepler argued in 1610, the night sky should be a wall of light, not a scattering of points against black. Since it obviously wasn't, something in the infinite model had to give. A finite, walled cosmos, dark beyond the last shell of stars, the same way a lit room stays bright, while the street past your window stays dark. He was wrong about the wall, but he'd correctly located the crack a full 2 centuries before anyone had the tools to explain it. A century later, Edmund Halley tried to wave the problem away, arguing that most stars were simply too faint to matter. The mathematics didn't agree with him. Now consider what actually happens as you add up truly faint stars by the billions, individually invisible, collectively enormous. A single candle a mile away contributes nothing to a dark room. 2 trillion galaxies worth of candles, at every distance, still sum to something. And in an infinite universe, that sum has no upper limit. Halley's faint stars didn't disappear from the equation. They just made the sky's projected brightness that much harder to explain away. In 1744, a Swiss astronomer named Jean-Philippe Loys de Chezeaux ran the actual numbers. The shells, the inverse square law, the whole infinite sum, and got exactly the answer the arithmetic demands: a sky at the brightness of the sun's surface in every direction. Chezeaux needed something to stop that light before it reached Earth, and he thought he'd found it. Vast clouds of interstellar dust, absorbing the light of the more distant stars before it could pile up into that blinding sky. Think of layers of frosted glass stacked in front of a lamp, each one dimming the light a little further. Dust, Chezeaux reasoned, was doing exactly that on a cosmic scale. An infinite universe wearing enough frosted glass to finally go dark. For nearly a century, that answer held. It was elegant, it matched the observations, and nobody yet had the physics to notice the one thing dust cannot do. Kepler had guessed the universe simply had an edge. Chezeaux had just proven, with real numbers, that an edge wasn't even the right kind of answer. Something about the light itself, not the geometry surrounding it, was still missing. Here's the part that changes everything about the dust explanation. Absorption is not the same as disappearance. When a cloud of interstellar dust absorbs starlight, that energy doesn't vanish. It heats the dust. And anything that heats up, given enough time, radiates that heat back out. Not necessarily as visible light, but as energy, somewhere in the spectrum. Given an eternal universe and infinite time for the process to run, the dust itself would eventually reach the same temperature as the starlight bathing it. It would glow exactly as brightly as the stars it was supposed to be blocking. You cannot hide an infinite amount of energy behind a curtain forever. Eventually, the curtain catches fire. Let that arrive slowly. Lord Kelvin was the physicist who finally said this out loud with real rigor. In 1901, already an old man by then, decades past the thermodynamic work that had made his name, still finding new cracks in a problem everyone else considered closed. He didn't reject the shell mathematics that Chezeaux and, later, the German astronomer Wilhelm Olbers had each rediscovered. Olbers published his own version of the paradox in 1823, and history, not entirely fairly, decided to name the whole problem after him instead of Chezeaux, who'd solved the hard part 79 years earlier. What Kelvin rejected was the escape hatch. dust couldn't save the infinite, eternal, unchanging universe. Something else had to give, and Kelvin pointed at an assumption nobody had seriously questioned yet, that the stars had been burning forever. They hadn't. Stars have a beginning, and if starlight itself has an age. If there was a moment before any star existed at all, then an infinite universe stops mattering, because you can't receive light from a source that hasn't switched on yet, no matter how much space you have to work with. Kelvin's insight had a second layer that took decades to unpack. Even granting an eternal universe, an eternal population of stars was a separate assumption, and untrue on its own terms. Stars are not permanent fixtures. They ignite, burn through a finite fuel supply, and go dark, some after a few million years, others after tens of billions. An endlessly old universe filled with stars that individually don't live forever isn't automatically the same as an endlessly old universe filled with eternal light sources. The paradox had quietly smuggled in two different kinds of infinity, and nobody had separated them yet. So now there were two separate cracks, not one. An infinite universe needed infinite time to fill every point of the sky with starlight. It also needed stars that never stopped shining to keep that sky filled once it finally caught up. Neither one, as it turned out, was true. That single sentence would turn out to be closer to the real answer than anyone in the room fully realized. But it would take a poet and then two confused engineers with a very good antenna to find out exactly how close. Kelvin had found the right kind of crack. He had not yet found what was hiding inside it. In 1848, a man deep in debt and already fighting the illness that would kill him within the year, rented a small hall in New York and delivered a lecture almost nobody wanted to hear. Edgar Allan Poe called it Eureka, and he insisted, against every one of his listeners' expectations, that it wasn't fiction. It was, he said, the actual structure of the universe. Delivered by a poet nobody in the room had come to hear lecture on physics. He gave the lecture at the New York Society Library to a room he'd hoped would fill and mostly didn't, and subtitled the piece, An Essay on the Material and Spiritual Universe. Grand, sincere, and exactly the kind of title that let the astronomers of 1848 assume they could safely ignore it. He reasoned it through without a telescope, without calculus, using nothing but a chain of logic he'd built alone. If the number of stars really were infinite, and light travelled at some fixed, finite speed rather than arriving instantly, then the sky's blackness had exactly one honest explanation. It wasn't that the far stars didn't exist. It was that their light hadn't gotten here yet. And in a universe with a real beginning, some of it, from the most distant reaches, never would. Not a wall of matter, stopping the light. A wall of time, light hasn't had long enough to cross. That single idea, an actual age to the universe, a real edge built from elapsed time rather than distance, arrived 80 years before any astronomer measured the universe expanding, and more than a century before anyone had a name for the event that started the clock. Poe got there with a fascination for infinity, and a stubborn refusal to accept the easy answers his contemporaries were satisfied with. And that edge, once astronomers finally confirmed it existed, turned out not to be fixed in place at all. A boundary that keeps receding as more time passes, always exactly 13.8 billion years behind whatever moment happens to be now. His contemporaries were not impressed. The audience that showed up expecting ravens and premature burials got a poet lecturing on cosmology instead, and most of them treated it as the sound of a brilliant mind finally coming apart. More than one review at the time couldn't decide whether it was criticizing a scientific claim or a literary indulgence, and settled for dismissing both. Poe self-financed the essay's publication as a small book, sold barely enough copies to cover the printing costs, and died 14 months later, in circumstances his biographers still argue about at 40 years old. He never saw a single piece of evidence that would have told him he'd been right. You know now exactly which wall he was pointing at, You've lived your entire life on the correct side of his answer. In that half-empty room in 1848, nobody did. He'd found the shape of the true answer using nothing but reasoning and an obsession with infinity that most of his readers mistook for delirium. It would take radio astronomers, an instrument built for something else entirely, and one very persistent noise nobody could get rid of, to finally hand him the proof he never lived to see. If this is the kind of night you return to, subscribe. The wall Poe never got to measure has a number attached to it now. 13.8 billion years, the entire age of the universe. Start to now. No line of sight, no matter how patiently followed, can carry information from anything further back than that. But there's a second wall hiding inside that number, sharper than simple age. A real stretch of time, early in the universe's own history, when the sky wasn't just unreachable. It was empty on purpose. There was nothing burning yet to see. For its first few 100,000 years, the universe was too hot and too dense for light to travel anywhere in a straight line. A fog of charged particles scattering every photon almost as soon as it was emitted. Then, around the 380,000 year mark, everything cooled just enough for electrons and protons to combine into stable atoms, and the fog lifted all at once. Think of steam fogging a bathroom mirror completely, then slowly clearing from the edges inward until the glass turns transparent in a single instant. The universe went through that same transition, once, on a scale that swallowed everything. Every photon that has ever reached your eyes from beyond our own galaxy is younger than that moment of first clarity. Nothing you have ever looked at in the night sky predates it. But clear didn't mean lit. The fog was gone. The stars hadn't arrived. For roughly the next 200 million years, matter drifted through fully transparent space with nothing yet burning inside it, clumping under gravity, slowly, patiently, with no deadline and no observer waiting. Astronomers call this stretch the cosmic dark ages, and the name isn't poetic license. No stars, not one, anywhere, for 200 million years of a completely transparent, completely lightless universe. Some astrophysicists describe it as the loneliest stretch in the universe's entire biography. Every ingredient necessary for starlight already present, none of it yet arranged correctly enough to switch on. A portion of the paradox, in other words, had already solved itself before anyone thought to look for the answer there. An infinite universe, filled forever with stars, has no excuse for a dark sky. A universe with a genuine dark age at the start of its history, a real epoch with nothing shining anywhere, has the simplest excuse there is. For that stretch of time, every line of sight really did end on nothing. Not because the star was too far away, because it hadn't ignited yet. That still isn't the whole answer. An old universe with a true beginning explains why the most distant stretch of sky can't be a wall of starlight. It says nothing yet about the light that came right after, the actual afterglow of the event that started the clock in the first place. That light didn't just vanish once the fog cleared. Something happened to it. And whatever that something was, it left a fingerprint that a pair of engineers would trip over, by accident, less than a century later. That first light didn't disappear. Not because it was blocked, or absorbed, or used up, because space itself has been stretching underneath it for 13.8 billion years. And stretching space stretches whatever light happens to be traveling through it at the time. Picture a wave drawn in marker across the surface of a deflated balloon. Peaks and troughs, evenly spaced. Inflate that balloon slowly, over hours instead of seconds, and the wave stretches with the rubber. The peaks end up farther apart than they started, even though nothing about the wave itself changed. Light works the same way, riding on the fabric of space instead of a balloon's surface. Stretch the space, and the wavelength stretches with it. And wavelength is what your eyes read as color. The light released when the universe first turned transparent started out glowing at something close to 3,000 degrees, a color somewhere between orange and white hot. After 13.8 billion years of that stretching, the same light arrives today at a temperature of 2.7 degrees above absolute zero. No longer orange, no longer visible at all, shifted so far down the spectrum that it now shows up as microwaves. The same broad family of radiation that carries a phone call or warms a plate of food, not because the afterglow of the origin of everything burned out, because it aged, the way sound drops in pitch as its source pulls away. Except this pitch has been dropping for the entire history of the universe, and it never fully stops arriving. Astronomers now call this signal the cosmic microwave background, the CMB for short, and it remains the oldest light any instrument has ever measured. Two physicists, Ralph Alpha and Robert Herman, had actually predicted a leftover glow like this back in 1948, 16 years before anyone detected it, estimating a temperature within a few degrees of the real value, using nothing but calculations about the early universe's density and cooling rate. Their predictions sat in the literature for over a decade, filed away as an interesting result nobody considered urgent enough to go test. That number, 2.7 degrees, is today one of the most precisely measured quantities in all of physics, confirmed independently by dozens of instruments since agreeing with each other to within a fraction of a percent. That signal is not a memory. It is not a metaphor for something older. Right now, while you're lying still and the lights are off, a faint bath of that exact radiation is passing through the walls of the room, through your body, in every direction at once, completely undetectable without very specific equipment. The oldest light in existence, still arriving, still landing on you 13.8 billion years after it left. It has been arriving everywhere, all at once, since roughly 400,000 years into the universe's existence. Two engineers at a research lab in New Jersey found it completely by accident in 1964, while trying to track down a source of interference in a radio antenna. And for months, their leading suspect wasn't cosmology. It was pigeons. Arno Penzias and Robert Wilson weren't looking for the origin of the universe. They were trying to calibrate a large horn-shaped antenna at Bell Labs in New Jersey, originally built for satellite communication for use in radio astronomy, and they kept picking up a faint, steady hiss they couldn't explain. The hiss showed up no matter which direction they pointed the antenna. It didn't fade during the day or strengthen at night. It didn't vary with the seasons, didn't track the Milky Way, didn't match any known radio source in the sky or on Earth. Standard troubleshooting suggested the fault had to be in the equipment, so they went looking for a fault in the equipment. They found one. Sort of. A pair of pigeons had been nesting inside the horn, and the accumulated droppings, described in Penzias's own notes, dryly, as a white dielectric material, seemed like a promising suspect. They cleaned the antenna thoroughly. They trapped the pigeons and had them relocated. The hiss remained, identical, unchanged, uninterested in the plumbing of the explanation they just ruled out. For a few strange months, one of the biggest open questions in the history of astronomy was filed. Informally, under bird problem. The actual answer had already been worked out on paper, 40 miles away, by physicists at Princeton who had no idea Penzias and Wilson existed. Robert Dicke, Jim Peebles, and their colleagues had independently predicted that a universe with a hot, dense beginning should leave behind exactly this kind of leftover radiation. Faint, uniform, coming from every direction at once, the red-shifted afterglow of the moment the universe first turned transparent. They were in the process of building an instrument specifically to go looking for it. A mutual colleague made a phone call. Dicke listened to what Penzias described, and reportedly turned to the rest of his team with 4 words. "Boys, we've been scooped." Penzias and Wilson had found the very thing an entire research group had been racing to build a detector for, using an antenna meant for satellites, chasing a noise they'd assumed was their own mistake. Neither man had set out to test a model of the universe's origin. They'd set out to fix a hiss, and ended up handing cosmology its cleanest piece of physical evidence, decades before either group had planned to publish anything. If you'd been standing beside that antenna in 1964, you wouldn't have noticed anything at all. The hiss lived entirely outside the range of human hearing, encoded in radio static that only the receiver, not the ear, was built to read. The discovery did more than confirm Poe's stubborn hunch and Kelvin's overlooked crack. It settled an argument that had split physicists for a generation. Between a universe with a genuine hot beginning and a rival model that claimed the cosmos had always looked roughly as it does now, with no starting point at all. Only one of those models predicted a leftover glow, in every direction, at exactly that temperature. The pigeons were innocent. The universe had a birth certificate, and it had been humming in the background the entire time. 13.8 billion years of travel time should put the most distant visible light exactly 13.8 billion light years away. That's the intuitive answer, and it's wrong. Because the space between here and there kept expanding for the entire time that light was already in transit, stretching the gap behind it, in front of it, and everywhere along the road it was still traveling. By the time that ancient light finally reaches a telescope on Earth, the galaxy that sent it is no longer 13.8 billion light-years away. It's closer to 46 billion light-years away, right now, carried outward by the same expansion that stretched the light itself into the microwave. Static 2 engineers once blamed on birds. Imagine a moving walkway at an airport that keeps getting longer while someone walks down it. New floor unrolling behind them, more of it unrolling ahead. Their walking pace never changes, but the starting point ends up much farther behind than footsteps alone could ever account for. And there's no contradiction in that at all. Just two different kinds of distance being measured at once. Astronomers have already named specific examples. In 2022, the James Webb Space Telescope identified a galaxy whose light left it when the universe was only a few 100 million years old. Light that has been traveling roughly 13.4 billion years to arrive here. That galaxy, if anything like its original form still exists, is no longer 13.4 billion light-years away. Current estimates put its present distance at somewhere near 33 billion light-years, carried outward by expansion for the entire time its light was crossing the gap. None of that motion happened at any single moment you could have pointed to and measured. It happened continuously, in increments too small to notice, spread across 13 billion years of your universe, rearranging itself underneath the light already in transit. Every edge astronomers describe is really two separate numbers layered on top of each other. How far the light traveled to get here, and how far away its source has drifted in the meantime. Both are correct. Neither one is the number casual arithmetic would predict, and mixing them up is the single most common mistake in every article that tries to describe the size of the universe in one sentence. That gives the observable universe a diameter of roughly 93 billion light-years, wrapped around a universe that is itself only 13.8 billion years old. Not a contradiction. A consequence of measuring a rapidly inflating balloon's surface from a single point glued to it. But that expanding edge carries a much colder implication than its size. If space is stretching everywhere, and stretching faster over greater distances, there should be a point past which the stretching itself outruns the light trying to cross it, a boundary where nothing that happens today will ever be seen from here. No matter how long anyone is willing to wait, that boundary exists, and it has a name, the cosmological event horizon, sitting today at roughly 16 billion light-years away. Past it, galaxies are receding from us faster than their light can close the distance. Not because anything is moving through space at an impossible speed, but because space itself is expanding fast enough out there that the gap grows even while the light is en route. Any photon leaving one of those galaxies tonight is already lost to us. It will travel for the rest of time and never arrive. Here's what almost nobody considers. This isn't a strange exception affecting a handful of remote galaxies. Dark energy is accelerating the expansion everywhere, which means that horizon is gradually swallowing more of the universe as time passes, not less. Galaxies we can see clearly tonight, catalogued and photographed, will eventually cross that boundary from our side. Their light won't stop existing. It will simply redshift further and further, dimmer and dimmer, until it fades below anything an instrument could ever recover. Not gone, just permanently, irretrievably out of reach. Olbers and Chezeaux spent their careers worried about a universe with too much starlight, forever, in every direction. The actual future runs the opposite direction entirely. Trillions of years from now, an observer standing where you're lying right now would look up and see almost nothing beyond a single merged smear of nearby galaxies. The rest of the universe not merely dark, but permanently erased from view, its light still traveling somewhere it will never arrive. The Milky Way itself is not exempt from that merging future. In roughly 4 to 5 billion years, it's expected to collide and merge with the Andromeda Galaxy, forming a single, larger galaxy some astronomers have taken to calling Milkomeda. That merged galaxy, together with a handful of small, gravitationally bound dwarf companions, is close to the entire inventory of what will still be visible once the wider universe finishes sliding past the horizon. Every other galaxy currently catalogued, imaged, and named eventually joins the light that already can't find its way back to us. Here's a tension tonight's narration isn't going to resolve, and isn't trying to. The same universe that makes you feel connected to something vast. 2 trillion galaxies, one shared origin, one shared afterglow still passing through this room, is also, right now, cutting that connection to almost all of it. Not someday, continuously, in the present tense. While you listen to this sentence, that paradox doesn't get a tidy answer tonight. We're going to sit inside it instead. The same way the sky sits, unresolved, between light that has already arrived and light that never will. What's left then is a narrower question than the one this video opened with. Not whether the whole sky should be ablaze, but why the visible slice of it looks the way it does at all. This particular version of dark at this particular moment in a 13.8 billion year story. Set aside the age of the universe, set aside the expansion, the redshift, and the slow erasure of galaxies sliding past the cosmological horizon. Even a universe granted genuine, literal infinity in every direction would still fail to produce Olbers' blinding sky. For a reason that has nothing to do with geometry at all. Stars die. A star like the Sun burns hydrogen for roughly 10 billion years before it changes character entirely. Far heavier stars burn through their fuel in a few million years and end violently. The smallest, coolest stars, red dwarfs, could in principle keep a dim fusion fire lit for trillions of years, far longer than the current age of the universe, but even they are not permanent. Proxima Centauri, the nearest star to the Sun, is a red dwarf like this, and it's expected to keep burning for roughly 4 trillion years, several hundred times longer than the universe has existed so far. Every star is, in the most literal sense, a temporary arrangement of matter doing something it cannot keep doing forever. An eternal, unchanging universe was never just a claim about space. It was, without anyone quite noticing, also a claim about starlight lasting forever. And that claim was false before anyone measured a single expanding galaxy. The paradox that Kepler, Halley, and Chezeaux inherited had smuggled in 2 different infinities: infinite space and infinite burning stars. And dismantling one without noticing the other would only have replaced one wrong answer with another. The dark between the stars was never empty. It's not simply late anymore either. It's temporary, a lit interval, sandwiched between two much longer stretches of true dark. The 200 million years before the first star switched on, and a future far longer than anything the last 2 hours have described yet. When the last stars burn out, the black holes finish evaporating on timescales too long to write down comfortably, and the sky goes dark again. This time for good. Put a real number on that timescale, and the comparison stops feeling like poetic exaggeration. The largest supermassive black holes are expected to finish evaporating through an extremely slow quantum process called Hawking radiation, only after roughly 10 to the power of 100 years. A figure so much longer than the current age of the universe that the two aren't meaningfully comparable at all. Hold that number for a moment. Everything tonight has described so far, the Dark Ages, the first starlight, the CMB still passing through this room, fits inside a sliver of time too small for you to meaningfully weigh against it. Star formation itself is expected to wind down over the next 1 to 100 trillion years, as the raw material for new stars is used up faster than it's replenished. What you're looking at on any clear night isn't the permanent condition of the cosmos. It's a comparatively brief, brightly lit chapter, the part of the story where there happens to be anyone around, on a planet, in the dark, to look up at all. Textbooks tend to present the resolution to Olbers Paradox as a single clean sentence. The universe is too young for the whole sky to be filled with starlight. That's true. And it's also an oversimplification real cosmologists still argue about, because the finite age of the universe, the cosmic dark ages, and the redshifting of ancient light out of the visible spectrum are three separate effects. Run the numbers assuming only a young universe with no expansion at all, and the sky would still be far darker than Chezeau's original nightmare, simply because there hasn't been enough time to fill every gap. Run them, assuming only expansion, with an eternal universe, and darkness returns for an entirely different reason. Distant starlight redshifts into invisibility, long before it can accumulate into anything blinding. Both effects are real. Both are measured, and specialists still debate which one deserves to be called the primary explanation in an introductory answer versus which one is merely a secondary correction. That disagreement sits inside a much larger, currently unresolved argument in cosmology, one with an actual name: the Hubble tension. Measurements of how fast the universe is expanding, taken from the leftover glow of the early universe, consistently disagree with measurements taken from nearby exploding stars and galaxies. Not by a rounding error, but by a gap large enough that most cosmologists no longer expect it to vanish with better instruments. Something in the model is either wrong or incomplete, and nobody currently knows which. Put real numbers on it. Measurements based on the leftover glow from the early universe put the expansion rate at a little over 67. Measurements based on nearby exploding stars, calibrated through a chain of closer, well-understood distances, put it nearer 73. That gap has held steady. In some analyses, widened, even as both measurement techniques improved for over a decade, which is exactly the pattern you'd expect if the disagreement reflects something real about the universe, rather than sloppy measurement on either side. If you ask 10 cosmologists which number is closer to correct, you would likely walk away with more than two answers. Some suspect an unknown, more exotic form of dark energy is required to bridge the two figures. Others suspect a subtle, uncaught error somewhere in the distance calibration chain. A smaller number wonder whether the standard model of cosmology needs a genuine rewrite. Tonight's darkness sits, unnoticed, right in the middle of that argument, because every one of those competing explanations changes. How much credit for an empty sky gets assigned to expansion rather than to age or starlight running out? None of this threatens the basic answer to tonight's question. The sky is dark because the universe is young, because starlight took time to arrive and more time to redshift out of view, and because the stars themselves don't burn forever, but the exact weighting of those causes. Which one to lead with, which one is merely supporting detail, remains an active argument inside the same field that considers Olbers Paradox solved. Even a settled answer, it turns out, can still have a live argument hiding underneath it. Kepler's original assumption that the universe was infinite, stretching in every direction without limit, is still, today, neither proven nor disproven. Not probably, pending better telescopes. Genuinely unknown, in a way most descriptions of modern cosmology gloss over, in a single confident sentence. Every measurement this story has described so far, the 93 billion light-year observable universe, the cosmological event horizon, the age of the first starlight, describes only the portion of the cosmos causally connected to Earth. What lies beyond that boundary is, by definition, information that has never reached us, and, in most cases, never will. Space could stop at some enormous but finite size just past our horizon. It could continue for another observable universe's worth of galaxies, and then stop. It could genuinely never stop at all. Current measurements of the universe's large-scale geometry are consistent with it being flat and infinite, but consistent with infinite is a very different claim from confirmed infinite. And the measurement uncertainty leaves room for a very large, merely finite universe hiding behind the same numbers. There's a related, stranger puzzle sitting inside the cosmic microwave background itself. The pattern of faint temperature variations across that ancient light should, under the simplest models, show fluctuation at every scale, including the very largest. Satellites built specifically to map the CMB in detail have instead measured slightly less variation at the largest scales than the standard model predicts. A small, persistent anomaly some cosmologists have connected to the possibility that space might wrap back on itself at some enormous but finite scale. The way the surface of a sphere has no edge without being infinite. Other cosmologists consider the anomaly a statistical fluke, a natural consequence of how few truly independent large-scale patches the observable universe actually contains to compare. Nobody has settled the argument either way. Whatever the true shape of space turns out to be, it was already out there, fixed, before you were born, before Kepler guessed wrong about it, before any of the Light into Night story started its journey. Only the guessing has changed. We still don't know, and tonight, that's exactly where this particular thread gets left. Not because the question is unimportant, but because it is one of the very few in this story that no amount of patience, no future instrument on any realistic timeline can currently promise to close. Every other mystery in tonight's narration eventually yielded to a name, a date, an instrument. This one, so far, hasn't. Kepler guessed wrong about where the universe stopped. Modern cosmology's honest answer is that it might not be able to tell you, even now, whether he was wrong to think it stopped anywhere at all. What can be answered? What the last 3 centuries of wrong guesses, accidental antennas, and one very stubborn poet actually did resolve, is smaller and stranger than the question of infinity, not how big the universe is. Why the particular sky above one particular planet on one particular night looks the way it does. Step outside on a genuinely dark, clear night, far from any city, and the naked eye can pick out somewhere around 2,000 to 3,000 stars at once, roughly 9,000 across the entire sky. If you could see both hemispheres simultaneously and count for as long as needed, that sounds like a great many points of light. Against the darkness surrounding them, it is almost nothing. Astronomers measure sky darkness in units built around how much light lands on a given patch of sky, and by that measurement, a good rural sky comes in at a brightness so low it takes long exposure photography, not eyes, to reveal how much truly dark area separates one star from the next. Even the combined light of every star visible to the unaided eye, spread across the entire dome of the sky, adds up to a small fraction of the glow of a single quarter moon. 2 trillion galaxies exist. Only a comparative handful of individual stars, all within our own, are close and bright enough for a human retina to register them as points at all. Astronomers even rank sky darkness on a 9-step scale called the Bortle scale, running from a blazing inner-city sky where only the moon and a handful of the brightest planets survive the glow, down to a Class 1 sky so dark the Milky Way can cast a faint shadow on the ground. Most people alive today have never stood under anything darker than a 5 or 6 on that scale, bright enough to wash out all but the most obvious stars, dim enough that almost nobody notices what's actually missing overhead. If you have ever travelled somewhere remote enough to see a genuine Class 1 sky, the difference isn't subtle. It looks like an entirely different universe was hiding behind the one you grew up under. Add up every star visible to the naked eye across the whole sky, and their combined light still comes in at only a small fraction of the brightness of a single quarter moon. Itself nothing more than a pale reflection of sunlight, not a light source in its own right. There is a faint, genuine background glow filling in the rest. Sunlight scattered by dust left over from the solar system's formation, a phenomenon called zodiacal light, plus a much fainter shimmer from the upper atmosphere itself, called airglow, plus the accumulated, unresolved light of every galaxy, too distant or too dim to register individually. Add all of that together, and the sky is still, overwhelmingly, dark. Not empty of contributions, just receiving almost none of them at any brightness the eye can use. Which puts a genuine number on tonight's paradox for the first time. Not the sky is dark, a vague description anyone could offer, but a sky measured at a specific tiny fraction of the brightness an infinite, unchanging universe would have produced. And every explanation traced so far accounts for a piece of that specific gap. Kepler wasn't the last astronomer to argue, in public, about where the universe stopped. In April 1920, at the National Academy of Sciences in Washington, 2 astronomers, Harlow Shapley and Heber Curtis, were the faint, spiral-shaped smudges visible through the best telescopes of the era, called spiral nebulae, clouds of gas inside our own Milky Way, or entire separate galaxies unimaginably far beyond it. Shapley argued for one large Milky Way, essentially the whole universe. Curtis argued the spirals were distant island universes in their own right, and that the Milky Way was only one galaxy among countless others. Neither man had decisive evidence, though both had real data. Shapley's case rested on something genuine. He had used the distribution of globular star clusters around the Milky Way to correctly estimate that our own galaxy was far larger than earlier astronomers assumed. Large enough, he argued, that it needed no neighbour to explain what telescopes were seeing. Curtis countered with a different kind of evidence entirely. A nova, a sudden stellar outburst, spotted inside the Andromeda Nebula, had appeared far fainter than novae observed within the Milky Way. If Andromeda were nearby, that faintness made no sense. If it were staggeringly distant, the numbers worked cleanly. Both men were partly right and partly wrong, arguing past each other with real observations that neither could yet interpret correctly. The debate settled nothing, technically, on the night it happened. 3 years later, working at the Mount Wilson Observatory, Edwin Hubble identified a particular kind of pulsating star, a Cepheid variable. Inside the Andromeda Nebula, Cepheids brighten and dim on a schedule directly tied to their true brightness, which meant Hubble could calculate exactly how far away this one had to be for it to appear as faint as it did. The answer, in 1925, was unambiguous. Andromeda was hundreds of thousands of light-years away, far outside the Milky Way by any reasonable measure. Curtis had been right. The universe was not one galaxy. It was, At minimum, billions of them. Hubble's Cepheid only worked as a distance marker because of a calibration built years earlier by Henrietta Leavitt, an astronomer working through thousands of photographic plates at Harvard, cataloguing exactly how a Cepheid's blinking period relates to its true brightness. Without her calibration sitting quietly in the record, Hubble would have had an interesting blinking star, and no way to convert that blink into an actual distance at all. You already know how this one ends, because you've spent the last several segments hearing about separate galaxies as an ordinary, uncontested fact. In that same Washington room in 1920, it was the single most contested claim in astronomy. Kepler had assumed the cosmos stopped at the edge of the visible stars. Shapley made almost the same mistake 3 centuries later, with better instruments and no better justification. Both times, the universe turned out to be dramatically larger than the person defending its limits was willing to imagine. And each time, a new tool, not a new argument, was what actually closed the case. Take the original nightmare seriously for a moment, as physics rather than thought experiment. A sky burning uniformly at the brightness of a stellar surface isn't just a bright sky. It's an environment in thermal equilibrium with the surface of a star, meaning everything under that sky, given enough time, heats up to roughly the same temperature. Not warm, roughly 5,000 degrees, hot enough to vaporize iron, well above the melting point of nearly every material a technological civilization would ever need to build anything at all, including the telescopes required to measure the paradox in the first place. However far away any given star's surface sits along a particular line of sight, in that universe every direction eventually intercepts one, meaning the sky itself functions as a container wall, radiating that temperature back at anything living underneath it. A genuine oven, with no door anywhere to open. Water boils away long before that point. Rock softens. The chemistry that makes a living cell possible falls apart at a tiny fraction of that heat, and falls apart everywhere at once, with no shaded side of any planet to retreat to, because the entire sky, from every angle, would be radiating like a furnace wall. There would be no night to cool the surface down. No cycle of light and dark for anything to adapt around. No dim, safe hours for anything resembling sleep to have ever evolved as a useful behavior in the first place. Whatever room you happen to be sitting in would offer no real shelter either. Walls block wind and rain, not thermal radiation arriving with equal intensity from every direction at once, including straight down through ground already glowing at the same temperature as everything above it. Not because darkness is simply pleasant, because darkness, at the scale the last 2 hours have been describing, is close to a precondition for chemistry complex enough to ask why the sky looks the way it does at all. There's a strange kind of loop hiding in that fact. Olbers Paradox is the puzzle of why the universe isn't blindingly, universally lit, and the honest answer is that if it were, there would be no eye, no mind, and no telescope left anywhere to register the contradiction. The universe had to stay dark enough, long enough, for something to evolve that could eventually ask the question. It was one of the conditions that made telling it possible at all. It's worth sitting with that trade for a moment. A universe that answers Olbers' Paradox cleanly, blazing, edge to edge, or a universe dark enough, for long enough, to have produced something capable of noticing the difference and asking you to consider it. Physicists sometimes describe this as a mild anthropic argument. Whatever the deeper reason turns out to be for a young, unevenly lit, expanding universe, a universe that failed to produce this particular kind of darkness would very likely have failed, first, to produce anyone in a position to complain about it. The cosmic dark ages didn't end quietly. When the first stars finally ignited, roughly 200 million years after the universe went transparent, they didn't just add a few points of light to an otherwise unchanged sky. They started a process that changed the chemical state of everything around them. Those first stars, astronomers call them population 3 stars, built from nothing but hydrogen and helium, with none of the heavier elements later generations would inherit, were almost certainly enormous, hundreds of times the mass of the Sun, and correspondingly furious. Stars that large burn through their fuel in a few million years, and while they burn, they flood their surroundings with ultraviolet light energetic enough to strip electrons from the neutral hydrogen atoms drifting between the earliest galaxies. Astronomers call this process reionization. It took several 100 million years to finish. Patchy and uneven. Some regions ionized early, others staying fogged in tens of millions of years longer, spreading through the universe star by star, region by region, like a slow-burning fuse lit in thousands of places at once. Nobody has ever directly observed one of these first-generation stars. So far, they remain entirely theoretical, reconstructed from models and indirect evidence rather than a confirmed photograph. Finding actual light from a genuine population 3 star remains one of the specific goals driving the deepest observations from the James Webb Space Telescope, the same instrument that measured the record-breaking ancient galaxy described earlier in Tonight. If it succeeds, it will be looking directly at the very stars that first tore reionization's path through the dark. Indirect evidence for this era is easier to come by than the stars themselves. Distant quasars, among the brightest objects known, show a specific pattern of absorbed light in their spectra. A dimming astronomers call the Gunn-Peterson trough. Whenever that light has passed through pockets of still neutral hydrogen on its way here, mapping where that pattern appears and disappears gives astronomers a rough timeline for when reionization finished in different directions of the sky, letting that light travel across enormous distances even without a single confirmed image of the stars that caused it. Before reionization, that intergalactic hydrogen would have scattered and absorbed much of the light trying to pass through it, the way fog scatters a headlight. After it, space between galaxies became transparent to visible light for the first time since the universe's original fog had cleared. A second, quieter transition, easy to miss next to the drama of the first stars themselves, but just as necessary for anything that came after to actually be visible across enormous distances. The first stars, in other words, didn't just light up the dark. Every photon reaching your eyes tonight from a galaxy beyond our own has been riding through that same cleared path, undisturbed, for the entire remaining span of cosmic history since. You are, in a very literal sense, looking through a tunnel those ancient stars dug once and never had to dig again. Penzias and Wilson found the leftover glow of the early universe by accident, with an antenna meant for something else. Confirming exactly what kind of glow it was took a dedicated satellite built for that single purpose called the Cosmic Background Explorer, COBE, launched by NASA in 1989. COBE carried an instrument designed to measure the precise spectrum of that ancient radiation. Not just its rough temperature, but the exact curve of brightness across every wavelength, the same kind of curve physicists use to describe an idealized object called a perfect blackbody. A perfect match to that theoretical curve would confirm, in extraordinary detail, that the signal really was the red-shifted afterglow of a hot, uniform early universe, exactly as the Big Bang model predicted. COBE carried 2 separate instruments for the job, not one. The first, called FIRAS, produced that blackbody curve. The second, called DMR, mapped tiny temperature differences across the entire sky, variations of only a few hundred thousandths of a degree, the faint imprint of density fluctuations that would eventually grow into every galaxy and every cluster massive enough to hold itself together under gravity. Those same tiny variations are the ones later satellites. And the large-angle anomaly described earlier in this story would go on to map with far greater precision. The result, presented in 1990, matched the theoretical curve so closely that when the lead scientists projected the data next to the prediction at a conference, The audience reportedly gave the graph a standing ovation, an unusual response to a piece of data, earned because the measured points and the predicted line were, at the scale of the chart, functionally indistinguishable. John Mather and George Smoot, who led the two instrument teams responsible for the measurement, shared the Nobel Prize in Physics in 2006, awarded specifically for that precision. If you've ever seen a textbook graph with error bars so small they nearly vanish into the line itself, there's a decent chance it's a version of this one. Picture standing in that conference room in 1990, watching a screen fill with a curve any physicist in the audience could recognize on sight, landing, point for point, exactly where theory said it should. You would understand immediately why people who don't often applaud data started clapping. The measurement did more than earn a prize. It closed the last serious scientific argument for a rival model of the universe. The same rival theory Penzias and Wilson's discovery had already wounded a quarter century earlier. Poe had guessed the shape of the answer with nothing but reasoning. Penzias and Wilson had stumbled onto its physical signature with an antenna and some very persistent pigeons. Kobe was the moment the signature stopped being merely detected and became measured with enough precision to leave. Essentially, no room left for doubt. Every gap tonight's narration opened about the universe's origin has, by this point, been measured, dated, and closed. It's a gap in what it actually feels like to live inside the timeline those measurements describe. Star formation across the universe was not steady. It rose, sharply. For the first few billion years after the cosmic dark ages ended, reached a maximum somewhere around 10 billion years ago, a period cosmologists sometimes call cosmic noon, and has been slowly declining ever since. As the raw gas needed to build new stars gets used up faster than it's replenished. Put a rough number on the decline. Most estimates put today's overall rate of new star formation somewhere between 1/10 and 1/30 of its peak value at cosmic noon. The universe isn't running out of gas everywhere at once. Some regions are still forming stars vigorously, but averaged across everything, the assembly line has already throttled down substantially, long before anything resembling a full shutdown. That means the current era, the one producing tonight's narration and the sky it's describing, sits well past the universe's peak brightness, on the downward side of a curve that will keep falling for a very long time to come. Not dramatically darker year to year. Nothing about that decline registers on a human timescale, or a civilization's timescale, or even most of a species' entire existence. But measured against the full future the last 2 hours have already sketched, against star formation continuing in a thinning trickle for another 1 to 100 trillion years before essentially stopping altogether, right now counts as early. Comfortably, unmistakably early. It helps to be specific about what early actually means here. Not early the way a sunrise is early in a day. Early the way a single word is early in a book running to hundreds of trillions of pages, most of them on current trajectories, containing steadily less light than the page being read right now. There's a strange kind of privilege hiding in that fact, one that has nothing to do with anything humanity did to earn it. Every star currently visible, every galaxy currently bright enough to register as more than a smudge, exists because you happen to be listening at a moment when there is still enough new starlight being produced to notice. Trillions of years from now, whatever kind of observer exists then, if any observer exists then at all, will look up at a sky far emptier than tonight's. Not because the universe grew stranger, but because it kept doing exactly what it's doing now, for a very long time, without you there to watch the tail end of it. Olbers worried about too much light. Forever. The actual shape of forever turns out to run the other way. What's above you tonight isn't the universe's steady state. It's closer to a brief flare, caught by pure accident of timing, by something capable of looking up and asking why it isn't brighter. None of this changes anything about tomorrow, or next year, or any span of time an actual human life will ever register. It changes only the answer to a much larger question. Tonight keeps circling back to whether the sky above you tonight is close to typical or close to a rare exception the universe will spend nearly all of its remaining history without. Cosmologists sometimes divide the universe's entire timeline into a small number of named eras, and the one containing every star this story has described so far, including the Sun, including every star visible tonight, is only the first of 4. This one is called the Stelliferous Era, the age of stars, running from the end of the cosmic dark ages to somewhere around 100 trillion years from now, when the last new stars finally finish forming and the existing ones burn down to embers. After that comes the Degenerate Era, spanning a length of time almost impossible to write in ordinary numbers. Stellar remnants, white dwarfs and neutron stars, slowly cooling and occasionally colliding, while protons themselves may or may not eventually decay, depending on physics not yet confirmed by any experiment. Physicists disagree about exactly how the Degenerate Era ends, because the answer hinges on whether protons are perfectly stable or decay after an almost unimaginably long half-life, a question no experiment has yet resolved either way. If protons do decay, ordinary matter itself eventually stops existing in any recognizable form, remnants included, dissolving slowly into radiation over a timescale longer than anything else named tonight. If they don't, dead stellar remnants persist essentially forever, cooling toward the same temperature as the space around them. Then, the black hole era, in which black holes, the last objects still producing any meaningful energy at all, slowly evaporate through Hawking radiation over timescales that dwarf everything described earlier tonight, including the 10 to the power of 100-year figure already mentioned for the largest ones. Finally, the dark era. Nothing left but a thin, cooling scatter of the lowest energy particles physics allows, expanding into a volume too vast for anything to ever interact with anything else again. Tonight's paradox, the one about starlight and blackness, only makes sense as a question during the first of those 4 chapters. Ask why the sky is dark during the dark era, and the honest answer stops being a paradox at all. It becomes simply, flatly, the correct and total description of everything that exists, every fact handed to you so far tonight. The antenna, the satellite, the poet, the galaxies sliding permanently past the cosmological horizon, belongs entirely to the first and by far the shortest of these 4 chapters. You have never lived, and could never have lived, anywhere else in this timeline. Every fact in tonight's narration so far, the dust that couldn't hide the light, the antenna that heard the universe's birth, the far edge steadily swallowing distant galaxies whole, describes a universe still early enough in its own story for darkness to be surprising. That won't stay true forever. It is, by a margin longer than any number in tonight's narration is comfortable saying out loud, already the exception. That's not a small detail tucked into an already strange story. It may be the strangest fact in it. Everything tonight has described, without exception, belongs to the brief, comparatively loud opening chapter of something almost entirely silent. Every star shines because of an imbalance, not a resource. Stars convert something highly ordered, matter arranged under enormous gravitational pressure, into something far less ordered. Heat and light, spreading outward, never spontaneously reassembling into the tightly packed fuel it started as. Physicists describe that one-way arrow with a formal name, entropy, and a rule that has no known exception anywhere it has ever been tested. Entropy increases, overall, in any closed system, without fail. Not because of any rule imposed on stars specifically, because it's the same rule governing why heat flows from something hot to something cold and never spontaneously reverses, why a cup of coffee left alone cools down and never spontaneously reheats, Why a shattered glass never reassembles itself off the floor. Stars are simply the largest, brightest example of that same one-directional process, running at a scale that lights up a solar system while it plays out, which means the very mechanism responsible for tonight's starlight is, simultaneously, a countdown. A star cannot produce light without spending down an ordered resource that cannot be replenished from the inside. Fusion buys enormous stretches of time, billions of years, for a star like the Sunday. But every one of those years is drawn from a finite account, and nothing about the physics allows a deposit back into it. The Sun alone spends down roughly 4 million tons of its own mass every second, converting matter directly into the light and heat radiating outward in every direction, a process it inherited fully formed at birth and can never refill or reverse. That countdown is not an abstraction happening safely far away. The warmth reaching your skin from any star, including the nearest one, is that countdown made physically tangible. Spent order, arriving as heat, on schedule, roughly 8 minutes after leaving the Sun's surface. This is not a special flaw in stars or a design failing to route around. It is the same imbalance responsible for nearly every interesting process in the observable universe, including the ones that make life, thought, and a person lying still enough to listen to a story like this one possible in the first place. Complexity, warmth, light, all of it rides on that same one-way arrow. Spending down order the universe was issued exactly once, at the very beginning, and has been steadily cashing in ever since. It's tempting to hear entropy described this way as bad news, a kind of cosmic decay working against everything. It is, without contradiction, also the exact process responsible for every warm, complex, temporarily ordered thing this story has touched. A star burning long enough for a planet to cool into something survivable. A body evolved to notice a night sky at all. A mind, not unlike your own, capable of turning that noticing into 3 centuries of increasingly precise wrong guesses. The imbalance doesn't only end things. On the way to ending them, it's what allows anything worth describing to have happened in the first place. Every explanation in tonight's narration so far has described a natural darkness built into the physics of an expanding, aging universe. There's a second, much smaller kind of sky brightening now, and this one is entirely artificial. Researchers who study night sky brightness estimate that something close to 1/3 of humanity can no longer see the Milky Way from where they live, drowned out not by starlight but by the scattered glow of streetlights, billboards, and windows reflected back down off the atmosphere itself. Sky glow, the term astronomers use for it, doesn't behave like natural background light. It concentrates over cities and spreads for tens of miles beyond them, thinning out the deep, textured dark that every explanation in the last 2 hours have assumed was simply available to look at. A widely cited atlas of artificial night sky brightness, built from satellite imagery, put a specific number on the scale of it. Across the United States and Western Europe, well over 3 out of every 4 people can no longer see the Milky Way from wherever they call home. If you have to drive somewhere specifically to find it, you already live inside that statistic. Observatories built decades ago, deliberately sited in what were then remote dark locations, now compete with sky glow from cities that have since grown out to meet them, degrading certain kinds of data in ways that can't always be corrected afterward, no matter how the telescope itself gets upgraded. A newer contributor has joined it directly overhead. Large satellite constellations, launched by the thousands over the past several years to provide broadband internet coverage, catch sunlight at dawn and dusk and cross the sky as bright, fast-moving points, sometimes invisible trains of a dozen or more. Astronomers running wide-field sky surveys have reported entire images ruined by satellite streaks crossing the frame during a single exposure, and the International Astronomical Union has formally raised concerns about the cumulative effect on both professional research and the ordinary experience of a dark sky. Current plans from several companies would eventually place tens of thousands of these satellites in low orbit, each one a small, bright, fast-moving point crossing the frame of any long-exposure image taken during twilight. Precisely the hours many surveys depend on. A single ruined frame might seem minor. Multiplied across a survey cataloguing millions of galaxies, the lost data adds up to a real scientific cost, still being negotiated, right now, between astronomers and satellite operators who mostly agree on the problem and still disagree on who should pay to fix it. There's a genuine irony sitting inside that fact. It took 3 centuries, a bankrupt poet, and an accidentally discovered signal from the birth of the universe to explain why the sky is dark in the first place. It's taking a single human generation, almost as an afterthought, to make it measurably less so. Not through malice or grand design, just the ordinary, unglamorous accumulation of streetlights and satellites. Nobody sat down to plan around a dark sky's survival. Every star named tonight, the Sun, Proxima Centauri, the population 3 giants that tore open the cosmic dark ages, belongs to a census that has never stopped changing. Stars are born, burn, and die on a rolling basis, and the number currently shining at any one instant is only a fraction of every star that has ever existed across the universe's full history. Astronomers can only estimate the true cumulative total, since nobody was counting in real time across 13 billion years, but the estimates involved run to a number so large it stops functioning as a quantity anyone can actually picture. Commonly cited figures land somewhere in the range of 1 billion trillion stars having existed at some point, across every galaxy, across the entire timeline since the first ones ignited. Most of those stars, especially the enormous, short-lived ones like the population 3 giants, are long since dead, their fuel spent in a few million years, their remnants scattered as neutron stars, black holes, or the heavier elements later folded into new generations of stars and planets. Consider the rate rather than just the total. A single galaxy like the Milky Way experiences a supernova, the violent death of a massive star, roughly once or twice per century. Multiply that modest-sounding rate across 2 trillion galaxies, and a star is ending, somewhere in the observable universe, several times every second, continuously outpacing the count anyone could keep by hand, whether or not any instrument happens to be pointed at it when it happens. Somewhere above you right now, while you listen to this, several such deaths are almost certainly already underway, their light still years or millennia from reaching any telescope capable of noticing. Every element heavier than hydrogen and helium. The calcium in bone, the iron in blood, the oxygen in every breath, was forged inside a star that has since died, its outer layers scattered by exactly this kind of violent ending. The stars currently shining are, in a real sense, only the visible surface of a much larger graveyard doing the actual work of building everything else. None of that arithmetic is visible from the ground. A night sky, however dark or bright, only ever shows the stars still actively converting mass into light, never the far larger number that already finished the job, quietly, sometime in the last 13 billion years, leaving only its ashes behind to be folded into whatever came next. The 2 trillion galaxies worth of starlight described at the start of this story, in other words, was never even the full inventory. It's the surviving fraction, the currently shining remainder of something that has been dying continuously, in the background, for the entire history of the universe, steadily outpacing the number of stars currently doing the shining. The atoms in your own body were, almost certainly, forged inside stars that no longer exist, meaning the very ability to hear this sentence depends on a stellar death that happened long before the sun itself had formed. Set aside stars, galaxies, and light entirely for a moment. Take the darkest, most thoroughly evacuated patch of space in tonight's entire story. The deep gap between galaxies, stripped of gas, dust, and starlight alike. And physics still refuses to call it empty. The underlying reason traces back to a basic limit in quantum physics. Certain pairs of properties, including energy and the amount of time available to measure it precisely, can never both be pinned down exactly at the same instant. That uncertainty isn't a limitation of instruments. It's a built-in feature of how the universe handles information at the smallest scales. And one consequence is that a perfectly still, perfectly zero-energy vacuum isn't a state nature actually permits, anywhere, under any circumstances physics has ever managed to test. Something is always, faintly, happening. Quantum theory predicts that even a true vacuum seethes with brief, unmeasurable in isolation fluctuations. Pairs of particles flickering into existence and vanishing again almost instantly, borrowing energy so briefly that no law is broken in the lending. For decades, this sounded like a mathematical formality, a bookkeeping quirk with no physical consequence anyone could actually detect. Then, in a laboratory, physicists measured it directly, placed two uncharged metal plates extremely close together in a vacuum, and they experience a measurable force pulling them together. The Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948 and confirmed with increasing precision since the 1990s, caused by the vacuum itself behaving differently between the plates than it does everywhere else around them. This same flickering vacuum is the mechanism behind Hawking radiation, the extremely slow process, already described earlier tonight, by which black holes are expected to evaporate over almost unspeakably long timescales. Near a black hole's boundary, one particle from a fluctuating pair occasionally falls in while its partner escapes outward, and over enough time, that slow leak is expected to drain even the most massive black hole down to nothing at all. None of this stays confined to laboratories or the edges of black holes. The same quantum vacuum fills the room you're lying in right now, indistinguishable, in principle, from the vacuum sitting in the coldest, most distant gap between galaxies. Your own body is held together partly by forces that continuously borrow from and repay that same underlying flicker without you ever noticing a thing. Not because the plates are doing anything, because the space between them isn't the nothing it appears to be. And nothing in this entire episode, from the gap between galaxies to the gap between two sheets of metal in a lab, has turned out to be describing a true philosophical absence at any scale, cosmic or subatomic. Darkness, at every level tonight's narration has examined. A room, a forest, an antenna, the space between galaxies, the space between two metal plates in a laboratory, keeps turning out to be a specific, active, measurable condition, rather than a blank default nature hands out for free. That flickering quantum vacuum ought to carry a specific, calculable amount of energy, and calculating it is exactly where modern physics runs into its most embarrassing unresolved number. Quantum field theory predicts a vacuum energy density by adding up the contributions of every possible particle fluctuation at every possible scale. Cosmological observations, meanwhile, measure the actual amount of energy filling empty space directly, through its effect on the universe's accelerating expansion. The same dark energy responsible for the cosmological event horizon described earlier in the last 2 hours. The two numbers should, in principle, agree, or at least land in the same neighborhood. Instead, the theoretical prediction comes out somewhere between 60 and 120 orders of magnitude larger than the measured value. A discrepancy so extreme that physicists sometimes call it, without much exaggeration, the worst prediction in the history of physics. This isn't the first time this particular kind of energy has caused trouble, either. Einstein introduced a term into his own equations in 1917, the cosmological constant, specifically to keep his model of the universe static, neither expanding nor contracting, matching the assumption astronomers held at the time. When later observations showed the universe expanding after all, Einstein reportedly considered the constant his own greatest blunder and dropped it. In 1998, Two independent teams studying distant exploding stars discovered the expansion wasn't merely continuing, it was accelerating, and the simplest explanation required bringing that same abandoned term back, this time as a real, measured property of space itself, not a convenient fudge factor. Try to hold the size of today's discrepancy in ordinary terms. 60 to 120 orders of magnitude isn't the gap between a rough guess and a slightly off measurement. It's closer to predicting the weight of a single grain of sand and getting back an answer heavier than every galaxy in the observable universe. Combined, more than once over, physics routinely predicts other quantities to 9 or 10 decimal places of precision. This is the same field, at its most successful, producing its single, least accurate number. Nobody currently has a confirmed explanation for the gap. Some physicists suspect unknown cancellations between terms nobody has correctly identified yet. Others suspect the calculation is missing an entirely new principle of physics, not yet discovered. The discrepancy sits, unresolved, underneath every single number in tonight that depends on dark energy or cosmic expansion, including the steady disappearance of galaxies past the cosmological horizon and the accelerating stretch that turned the universe's first light into microwave static. Whatever eventually resolves, it will likely reshape more than one number already used tonight. The size of that horizon, the rate at which distant galaxies keep sliding permanently out of reach, even the timeline for the universe's final, darkest era. Tonight's paradox turned out to have a real answer. One you now have in more detail than most people who have ever wondered about it. The energy of empty space, the thing partly responsible for that answer, does not yet, and not by a small margin. Whatever you take from the rest of this story, that unresolved number sits underneath most of it, unglamorously, waiting. Not every response to disappearing darkness has been passive. A non-profit organization founded in 1988, now operating internationally under the name Dark Sky, spends its time doing something that would have sounded strange to most of the astronomers in this story's history: certifying places specifically for how dark they still are. If you've ever driven far enough from any city to see the Milky Way arch overhead as an actual structure, rather than a rumor, there's a reasonable chance you are standing inside one of these certified sites without realizing it. The designation exists precisely so that experience doesn't have to depend on luck. The certification process measures actual sky brightness, checks lighting policy, and rates locations against a formal set of criteria before designating them as dark sky parks, reserves, or sanctuaries. A title now held by sites on nearly every continent, from remote desert reserves in Namibia to state parks in the northeastern United States that draw visitors specifically to lie back and see a sky most of them have never encountered before. Some of these places see their overnight visitor numbers rise substantially once the designation is announced, driven by people willing to travel specifically for an experience their own hometown sky can no longer offer. The push isn't only about telescopes or tourism. Research into artificial light at night has connected it fairly directly to disrupted melatonin production and measurably worse sleep in humans and in a wide range of other species whose internal clocks evolved entirely around a reliable, predictable cycle of true dark. The same darkness this story has spent an hour explaining scientifically turns out to be something the body also depends on directly, in ways that have nothing to do with paradoxes or physics at all. Whatever helped bring you towards sleep tonight was very likely a dimmer, quieter room. The same basic ingredient astronomers spent 3 centuries fighting to explain, doing exactly what it has always done for a nervous system built to expect it. Some of the fixes involved are almost absurdly simple. Shielded streetlights that direct light downward, onto the road, instead of spraying it sideways and upward into the sky, cut light pollution substantially without reducing visibility for drivers or pedestrians at all. A change several cities have already adopted at minimal cost, once someone actually measured what the old fixtures were wasting. The retrofit typically pays for itself within a few years in reduced electricity use alone, before counting the darker, more legible sky, it happens to restore as a side effect nobody had to budget for separately. None of it requires new physics, new telescopes, or a single fact tonight's narration hasn't already covered. Only the decision to point the light where it's actually needed. 3 centuries after Kepler first noticed the sky wasn't behaving the way an infinite universe demanded, protecting what's left of that same dark sky has become, in a very small and practical way, a shared civic project, running quietly in the background of towns that mostly never think about Olbers Paradox at all. The photons are the same, starlight is starlight, and the physical sky outside tonight is made of the same basic ingredients Kepler argued about in 1610. What has changed completely across 4 centuries is what that darkness means to whoever happens to be looking at it. Kepler worked entirely with naked eye observation and geometry, without a telescope of his own good enough to settle the question, arguing from logic and a stubborn refusal to accept an infinite universe that couldn't explain what he saw overhead. Every generation after him inherited slightly better instruments and used them to shave a little more uncertainty off the same basic mystery until a satellite built specifically for the purpose could measure the answer's signature to a precision neither Kepler, nor Poe, nor even Penzias and Wilson had any real way to imagine. Kepler saw a genuine mystery, sharp enough to argue about in print, and reached for the only tool available to him, an assumption about where the universe stopped. Poe saw the same mystery, reasoned his way disturbingly close to the real shape of the answer using nothing but logic, and died without a shred of evidence to back him up. Penzias and Wilson stood underneath essentially the same sky, picked up its oldest secret by accident, and spent months blaming pigeons before realizing what they actually had. Cope's instruments measured that same signal down to a precision so fine the resulting graph earned a standing ovation. Every one of them was looking at the same basic darkness. None of them was seeing the same thing. The instruments changed. The basic human posture. Looking up, noticing a discrepancy, refusing to let it go unexplained. Never did. None of them were wrong to wonder, and none of them had access to the full picture at once, each one holding a single piece, certain it was the whole shape, unaware of how much still sat past the edge of what their instruments, or their century, could reach. Halley had faint stars and a hunch. Shazo had the correct arithmetic and the wrong culprit. Kelvin had the right kind of crack and no way yet to look inside it. Stack all of their partial answers on top of each other in order, and only then does anything like a complete picture start to form. That's worth sitting with directly. The sky itself has barely changed. On any timescale, a human lifetime can register. Almost everything about tonight's episode has been the story of understanding catching up to a fact that was already sitting there, unchanged, the entire time. Waiting less for the universe to reveal something new, and more for someone patient enough, eventually, to ask the right version of the question. You are, at this exact moment, looking at the most thoroughly explained version of that darkness anyone in this story ever got to see. The original question has a real answer now. Assembled from every piece the last 2 hours have laid out, the sky is dark because the universe is young enough that starlight from its earliest stretch hasn't had time to arrive. It is dark because a genuine stretch of cosmic history, the Dark Ages. It is dark because the light that did arrive from the most ancient sources has been stretched by expansion into wavelengths no eye can register. It is dark because stars themselves are temporary, burning down an inheritance of order they can never refill. 4 separate, independently confirmed mechanisms, each contributing its own share, none of them requiring a wall of matter, a curtain of dust, or an edge to space itself. You now know more precisely why the sky over your own head looks the way it does tonight than Kepler, Halley, Chezo, or Olbers ever managed to figure out in their entire lifetimes combined, and more than most people who will ever bother to ask the question at all. That answer is complete enough to close the question Kepler opened in 1610. It is not complete enough to close everything tonight has actually been circling. Segment 9 named a tension this story was never going to resolve. And it hasn't. The same universe responsible for the sense of belonging running underneath tonight's narration. One shared origin, one shared afterglow still drifting through this room, is also, continuously, sliding most of its own galaxies permanently out of reach, across a horizon expanding faster than light can ever cross back. That tension hasn't loosened as the episode went on. If anything, it's tightened. The heat death waiting at the far end of the universe's timeline, the vacuum energy discrepancy nobody can currently explain, the horizon quietly erasing entire galaxies from view, all of it points the same direction, toward a universe that connects everything at its origin and then spends the rest of forever pulling that connection apart. You are living inside that pulling apart right now, at a moment early enough that most of it is still invisible, still unfelt, still nothing more than a number in an astronomer's calculation rather than a change anyone could actually notice. That's the closest thing to comfort this particular tension is going to offer. Not a resolution, but good timing. The same good timing that applies to every star currently burning, every galaxy currently visible, and everything else tonight's narration has described as temporarily rather than permanently. Here, the last 2 hours isn't going to resolve that either. Not because the answer is unknown, in the way the shape of space beyond the horizon is unknown, but because some tensions aren't puzzles waiting for a missing piece. They're simply what it feels like to be a temporary, connected thing living inside a universe built, at every scale examined tonight, around gradual separation. The honest response isn't a solution. It's sitting inside it. A little longer, before the story closes. Look back over everything tonight has actually explained, and a pattern sits underneath all of it that has nothing specifically to do with darkness. Kepler thought he was arguing about geometry. Poe thought he was arguing about infinity. Penzias and Wilson thought they were arguing with a pair of pigeons. Every one of them was actually describing the same underlying quantity, from a different angle, without fully realizing the others were circling it too. The dust that couldn't hide starlight failed because of time. The cosmic dark ages were a genuine absence of stars, measured entirely in units of time elapsed since the universe's beginning. The red-shifted afterglow reaching this room right now is old light, defined by the amount of time it has spent stretching across an expanding gap. The stars burning out, the black holes evaporating, the last light fading past an ever-growing horizon. Every one of those is a statement about time, dressed up as a statement about brightness. Empty, across this entire episode, never once meant nothing is there. It meant not yet, or no longer, or not from here, not yet. 3 different flavors of a single condition. A gap between something happening and the information about it actually arriving. The 200 million years before the first star was a not yet. The galaxies sliding past the cosmological horizon are becoming a no longer, one photon at a time. The light from beyond the observable universe, if any exists out there at all, even the 200 million tons of hydrogen and helium fusing inside a star at any given moment, are only ever mid-sentence, releasing a story that will keep arriving, in pieces, for as long as that star keeps burning. Every fact you've been handed tonight, if you trace it back far enough, reduces to some version of that same accounting. How much time has passed? How much of it the light has had to travel? How much of it is still owed? Nothing in this story was ever a story about what does or doesn't exist out there. It was a story about arrival, about which parts of an already existing universe have reached far enough, in time, to be counted, and which parts are still, quietly, on their way, somewhere out past tonight's horizon, with nowhere else to be. Kepler assumed the universe had an edge, in space. It turned out to have an edge in time instead, one that keeps moving, keeps admitting new starlight into view, and keeps losing old starlight to expansion, simultaneously, forever. Tonight's paradox was never really a question about how much matter fills the universe. It was a question about how much of that matter's story has had time to reach the one place capable of asking about it at all, and how much is, even now, still somewhere out there in transit. Go back to the very first thing tonight's narration said. Before any of the history, the physics, or the accidental antenna, there are 2 trillion galaxies above you right now, full of stars that have never stopped burning, and the sky between them stays completely black. That sentence is still true. Nothing about it needs correcting. And nothing about it ever will. What's changed, permanently, is everything underneath it. Every assumption about what black actually means, replaced, piece by piece, segment by segment, with an answer built from real measurements, instead of guesswork about walls, dust, or an eternal, unchanging cosmos that never existed in the first place. Every promise made at the very start of tonight's narration has, by this point, been paid in full. The 3 explanations that seemed airtight and collapsed. Kepler's wall, Halley's dismissal, Chazot's dust. Each fell for a specific, named reason. Bell Labs and the 2 engineers who blamed pigeons turned out to be exactly where the universe's oldest light was finally caught red-handed. And the wall, 13.8 billion years wide, promised in the opening minutes, turned out to be built from nothing more exotic than elapsed time itself. The same elapsed time responsible for every other answer tonight handed you afterward. The dark between the stars isn't empty. It's just late. An old, worn phrase from earlier in this story was already reaching for something true. It undersold the case. The dark between the stars was never empty. And it was never simply late, as if some appointment had been missed. It was only ever early. Every gap in that sky, either a story that hasn't finished travelling yet, or a story already too far gone to ever arrive at all. And both of those are a kind of information, not an absence of it. Kepler wanted a wall he could point to. Poe wanted more time than his own century was willing to grant the universe. Kelvin wanted a beginning nobody before him had taken seriously enough. Penzias and Wilson, less ambitiously, just wanted their antenna to stop making that noise. Every one of them, without realizing it, was asking the same question a different way. How much of the universe's story has actually reached this particular point in space? At this particular moment, and how much is still somewhere out there, unarrived? Tonight's answer is the same for every one of them, separated by centuries and by entirely different tools. Some of it has arrived, most of it, by any reasonable accounting, has not, and won't, not for a very long time, if ever. You started tonight's narration being told the sky was full of stars and somehow still dark. You're ending it knowing that both halves of that sentence were always true simultaneously, for reasons that took 3 centuries, several careers, and one very confused pair of engineers to fully untangle. Nothing about the sky itself changed to make that possible. Only the amount of accumulated time, evidence, and stubborn attention available to look closely enough at it ever did. Every episode about the universe promises a journey, and most of them mean an actual, physical one. A trip outward, planet to star to galaxy, farther and farther from home. Tonight's journey never left the sky directly overhead. It moved along a completely different axis instead, not outward through space, but backward and forward through time. That's an unusual shape for a story about the universe to take. Most journeys, in life or in narration, move in one direction, gathering distance or information as they go. Tonight's map doubled back on itself deliberately, walking to the very edge of the universe's timeline and then walking the entire way back, picking up a different piece of the puzzle on each pass until the 2 directions met in the middle of a single, coherent answer. No other shape would have worked nearly as well. A story told only forward, from Kepler onward, would have read as a list of increasingly clever guesses. A story told only backward, from tonight's antenna signal to the Dark Ages, would have read as a technical report with no reason to care. Walking it in both directions at once is what turned a plain sequence of dates and names into something closer to an actual arrival, landing back in the same room it started from. The trip started in this room. Tonight, with an ordinary dark sky and a question that sounded almost childish once it was said out loud. It moved backward through Kepler's study in 1610, past Chezo's shell calculations in 1744, past Kelvin's lecture hall in 1901, back through the cosmic dark ages to the universe's first clear light at 380,000 years old, and further still to whatever came before that first instant. The last 2 hours never had the tools to describe. Then it reversed, travelling forward again through Poe's half-empty lecture hall in 1848, through the Great Debate in Washington in 1920, through Bell Labs and its confused pigeons in 1964, through Cobb's standing ovation in 1990, past cosmic noon roughly 10 billion years ago, through the satellites and streetlights gradually dimming tonight's own sky, and out toward a future measured in numbers tonight could only gesture at, rather than fully picture. The last stars, the last black holes, the last thin scatter of particles cooling toward nothing at all, somewhere past every date this story has actually been able to name out loud. That's the real shape of tonight's map. Not a line drawn across space, but a line drawn across roughly 14 billion years, walked in both directions, arriving back exactly where it started. A dark sky, overhead, now carrying a complete history instead of an open question. Every other episode about the universe moves you outward. This one moved you through time instead, and left you in the same physical spot the whole way through. The same room, the same sky, the same quiet dark, carrying a great deal more history than it did an hour ago. Set the entropy, the horizons, and the unresolved vacuum energy number aside for a moment. There's a warmer fact sitting underneath all of tonight's cooler physics. Easy to miss in a story this focused on darkness, distance, and things sliding permanently out of reach. It doesn't cancel any of that coldness out, and it isn't meant to. It simply sits alongside it, equally true, equally worth carrying into sleep tonight. Every atom heavier than hydrogen and helium in your body. The carbon, the calcium, the iron carrying oxygen through your blood right now was forged inside a star, most of them stars that finished burning long before the sun itself condensed out of the same dark, patient cloud of gas this story described drifting through the cosmic dark ages. That's not a metaphor reached for to end an episode gently. It's the same plain physical mechanism as everything else described tonight. Matter, processed inside stellar cores, scattered outward at the end of a stellar life, gathered back together by gravity into planets, oceans, and eventually, something capable of lying still and listening to a story about where it all came from. The 2 trillion galaxies that opened tonight's narration and the atoms currently keeping you breathing were never separate subjects. They were the same material, at different points along the same 14 billion year timeline. Some of it still burning inside a star tonight. Some of it already scattered into planets, oceans, and whatever is listening to these words right now. The darkness between the stars isn't a barrier keeping anything apart from that material. It's the space that same material has been quietly crossing for billions of years to become you in the first place. The mechanism responsible has a name and a paper trail. Stellar nucleosynthesis, worked out in detail by a small group of physicists. Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. It described, step by step, exactly which elements form inside which kinds of stars, at which stage of a stellar lifetime, and exactly how those elements get scattered back into space once that star's life ends. A full accounting nobody had assembled correctly before that single paper. It is, in its own quiet way, every bit as important a piece of tonight's story as anything measured by Kobe or Hurd. First, through a very confused pair of engineers. Nothing about that fact resolves the paradox that opened tonight's story. It isn't supposed to. It's simply what was true the entire time. Underneath the dust, the antenna, the horizon, and the unresolved number physics still can't explain. The same hour this channel has been pointing toward since the very first sentence. Confirmed. It was already true while Kepler argued with diggers, centuries before either of them could have known it. And it has stayed true for exactly as long as there has been anything made of atoms at all. Step outside again tomorrow night, weather allowing, and the sky will look exactly the way it always has. The same scattering of visible stars, the same wide, quiet, dark filling in everything between them. None of tonight's explanations will be visible in that view. No line will appear separating the light that has arrived from the light still on its way. No number will hang in the air, marking the edge of the observable universe, or the far edge steadily swallowing galaxies whole, or the 200 million years of true dark sitting at the bottom of it all. Every fact in tonight's story is true regardless of whether anyone remembers a single one of them by morning. The dust still couldn't have hidden that much light. The Dark Ages still happened. Once, for real, at the very start of everything. The antenna at Bell Labs still picked up a sound 2 engineers spent months blaming on birds. None of it depends on being recalled correctly, or recalled at all, to keep being the actual, physical reason the sky over any given rooftop looks the way it does tonight. That's fine. That was always going to be true. Understanding why the sky is dark was never going to make it look any different. The same way understanding why someone falls asleep the particular way they do doesn't change the shape of their breathing. The value of tonight's answer was never in what it changes about tomorrow's sky. It was in what it changes about the version of you looking up at it. That's a strange kind of gift for a science story to hand over at the end. Most explanations feel like they've used something up once understood. A magic trick loses something real the very moment its mechanism finally becomes visible to the audience. Tonight's paradox doesn't work that way. Knowing exactly why the sky is dark doesn't drain the sky of anything. If anything, the 200 million years of true dark, the antenna, the horizon, and the unresolved number sitting underneath dark energy all add weight to a sky that used to be, at best, simply pretty. Pretty was never going to be enough to explain why a bankrupt poet, a pair of physicists, and 3 centuries of astronomers refused to leave it alone. Understanding it properly turns out to be the more restful option, not the more complicated one. The difference between falling asleep under a mystery and falling asleep under an answer that happens to still feel, gratefully, like one. Kepler looked up and saw a contradiction he had no way to close. Poe looked up and saw a hunch he never lived to confirm. You get to look up tonight. And every night after, at the same physical sky, carrying an answer 3 centuries and dozens of careers in the making. Not a different sky, but you, standing underneath it, in a different way than you were before tonight. Kobe proved the leftover light from the early universe matched a near-perfect blackbody curve. It didn't have the resolution to turn that proof into a precise age for the universe itself. That job fell to a later mission, the Planck satellite. Launched by the European Space Agency in 2009 and operating for 4 years afterward, mapping the same cosmic microwave background in far finer detail than any instrument before it. At wavelengths and angular resolutions Kobe's original hardware was never built to reach. That same Planck data is also the source of the Hubble tension described earlier in this story. The stubborn disagreement between the expansion rate measured from this ancient light and the rate measured from nearby exploding stars. The 2 numbers disagree by a small but real margin, and that margin only became sharp enough to argue about once an instrument this precise existed to measure the CMB side of the comparison. Better measurement didn't resolve the puzzle. It's what made the puzzle impossible to ignore in the first place. Planck's data pinned the universe's age at 13,787,000,000 years, with an uncertainty of only around 20 million years either way. A precision better than 1 part in 700, achieved by measuring the faint, grainy pattern of temperature variations across the entire sky and comparing it against a detailed model of how those variations should have evolved since the moment they were imprinted 380,000 years after the beginning. That number is the actual figure underneath every 13.8 billion years, mentioned earlier in tonight's narration, a rounded shorthand for something measured with far more precision than the rounding suggests. The Dark Ages, the red-shifted afterglow, the slow erasure of galaxies past that same horizon, all of it rests on this single, carefully measured age, refined generation after generation of instrument, from Hubble's rough estimate in the 1920s, to Cope's confirmation in 1990, to Planck's fraction of a percent precision 2 decades later. Kepler had no way to put any number at all on how old the universe was. He didn't have the concept available to ask the question in those terms. Whatever the sky looked like to him in 1610, it was already 13,787,000,000 years old. Whether or not a single person alive at the time had any way to check, you, tonight, are hearing that number stated with a confidence interval smaller than the rounding error most people carry around in their own birth year. It's worth pausing on the strangeness of that fact by itself. A civilization that still argues about plenty of things has nonetheless agreed, across dozens of independent instruments and research groups, on the age of absolutely everything, down to a margin smaller than most people's uncertainty about their own commute time, a number you can now recite more precisely than the astronomers who spent their entire careers chasing it ever actually could. In their own lifetimes, look at the pattern running underneath every discovery in the last 2 hours. And it isn't cleverness, exactly, or even luck. It's a specific, repeatable willingness to let a measurement overrule what seemed obvious beforehand. Chezo ran the shell arithmetic honestly, even though the answer it produced, a sky as bright as the sun in every direction, contradicted the sky he could see with his own eyes every night. He didn't discard the math to protect his intuition. He looked for what the math demanded must be missing instead, and reached for dust, which turned out to be wrong, but for entirely defensible reasons given what was known in 1744. Being wrong for a good reason, honestly reasoned through, moved the problem forward in a way that dismissing the paradox entirely never would have. Kepler trusted the darkness he could see over the beautiful, symmetric infinity Diggers had proposed. Hubble trusted a single blinking star's calculated distance over an entire Academy's confident assumption about the size of the Milky Way. Penzias and Wilson, to their considerable credit, kept chasing a signal that made no sense rather than writing it off as equipment noise once the obvious suspect. The pigeons turned out to be innocent. Every one of them had a simpler, more comfortable story available. Every one of them set it aside because the data refused to cooperate with it. That pattern matters more than any single fact tonight has handed you, because it's the only piece of tonight's story still fully in your hands. The paradox itself is solved. The mechanism is measured, dated, and confirmed by independent instruments that agree with each other. What isn't finished is the next observation that won't fit the current model cleanly, the next Hubble tension, the next vacuum energy discrepancy, the next faint signal. Somebody's first instinct will be to blame on pigeons. Every unresolved number this story has flagged along the way, the expansion rate disagreement, the vacuum energy discrepancy, the large angle anomaly hiding in the CMB itself, is currently sitting on someone's desk in exactly the position Olbers Paradox once sat on Kepler's, waiting for whoever is stubborn enough to trust it over their own expectations. None of tonight's history suggests that person needs any special credential to be the one who eventually notices. Kepler was an imperial mathematician arguing with a gentleman astronomer. Poe was a poet with no formal training in physics at all. The pattern has never required permission, only attention, patience, and a genuine, stubborn refusal to let a strange result go unexplained indefinitely, however long it eventually took. Nothing about tonight's story required genius that isn't ordinarily available. It required people willing to sit with a genuine discomfort, a sky that shouldn't be dark, a distance that shouldn't work out, a hiss that wouldn't go away, for long enough to let the answer arrive on its own schedule rather than the schedule anyone would have preferred. The sky is dark tonight, not because the universe is empty, but because it is young enough that starlight from its farthest reaches hasn't had time to arrive, because a genuine 200 million year stretch at the very start of everything had no stars in it at all to shine, because the oldest light that did arrive has been stretched by an expanding universe into colour no eye was ever built to register, and because every star currently burning overhead is spending down an inheritance of order it can never refill, on a schedule that ends the same way for all of them. The universe was never contradicting itself. Full of stars and completely dark were never actually in conflict. They were two different measurements of the same 14 billion year old fact, taken from two different distances in time, one counting what exists, the other counting what has, so far, managed to arrive. What's still unresolved stays open, quietly, past tonight the way it always has. The true shape of space beyond the horizon, the energy hiding inside genuine emptiness, the slow, permanent separation of everything tonight's narration called ours from almost everything else it counted. None of that gets tied off with tonight's answer. It was never going to. We've drifted, tonight, from an ordinary dark sky backward through 3 centuries of wrong guesses and one very stubborn poet, down into the cosmic dark ages, out along a horizon that keeps sliding galaxies permanently out of reach, and forward again into a future far quieter than anything overhead right now. We've sat inside an antenna's confused hiss, a satellite's standing ovation, a debate about whether the Milky Way was the whole universe or just a single room in a much larger house. Together, we've traced a single question all the way back to its source and most of the way out to its end, picking up a little more of the dark's actual shape at every stop along the way. You were never separate from any of it. The atoms keeping you warm tonight came from the same stars this story has spent the last 2 hours describing, and the same darkness that once looked like an unsolved contradiction to Kepler, to Poe, to 3 centuries of people lying awake wondering about it, is, at this exact moment, doing the ordinary work of helping you rest instead. If your eyes feel heavy, let them close. That was always the point. If this felt like home, leave a comment when you wake up. If you're still here, the next chapter is waiting. There are still 2 trillion galaxies above you right now, full of stars that have never stopped burning. The sky between them is still completely black. That was never a contradiction. It was, this whole time, an answer. Arriving exactly on schedule. The universe will still be here when you wake up. So will we. Good night.